Hello guys, in today's lesson we are going to consider the origin of the universe. Now, if you look at this picture here, you will notice a spot, very bright and white, and then different color changes, and then at this stage we have different kind of objects like the galaxies and so on. This is simply the model of the universe, and this point is how the universe look as of today. In the course of the lesson, we are going to look at or attempt to answer the following questions. What is the universe? How did the universe come to existence? Does the universe have an end? Does the universe have an outside? Now, the first and second questions can be answered by science, but the third and the last questions are not questions that science can answer. Now, this is because we don't have the technology as it is today to be able to ascertain or determine if the universe is finite or infinite. What's the universe? The universe is anything that exists. It's all of the space and time. All the stars, the planet, moons, comets, asteroids, meteors, and everything else. Now, the extent of the observable universe is about 93 billion light years in diameter. That means looking at one end or one side, here you'll be able to see half of 93 billion light years ahead of you. Now, looking behind, you'll be able to see as much as half of 93 billion light years behind you. The Big Bang. The Big Bang theory attempts to answer the question, how did the universe come to existence? The universe begins at about 14 billion years ago. At this stage, the universe expanded from something very small, smaller than an atom, very small with infinite temperature and energy. That is, it's hotter than anything that you can imagine. In a fraction of a second, the universe grew to the size of a galaxy and has continued to expand ever since. Now, as it expands, it cools off, and energy gradually transforms to particles like hydrogen and helium. These particles combine to form the stars or galaxies that we have. Evidence of the Big Bang. There are several evidence of the Big Bang theory. We have two of them here, the redshift and the cosmic microwave background radiation, which is otherwise called the CMBR. Now, to understand the redshift, we need to understand the speed and wavelength of the different spectrum of white light. Now, when white light enters a prism, it travels, the different colors of white light travel at different speed in the prism, and as such emerges or split or dispersed into different colors when it emerges outside the prism. Okay, this separation of colors is what otherwise called the spectrum of white light. We have 7 colors in the spectrum of white light. We have the red, the orange, the yellow, the green, blue, indigo, and violet. The red color is the least deviated, while the violet is the most deviated. This implies that the red color traveled fastest in the prism, is the fastest one in the prism because it's the one that emerged first, while the violet is the slowest in the prism. Okay, the red part of the spectrum have a longer wavelength. Recall that speed is proportional to wavelength. So the red colored light part of the spectrum is about 750 roughly nanometer in wavelength, while the violet has the lowest wavelength. Okay, it implies that the blue colored light should have a wavelength that is quite smaller than that of the red colored part of the spectrum. Hydrogen gas absorbs light of different wavelengths in the spectrum to form bands or lines called absorption line. This usually happens when you pass hydrogen vapor through the spectrum, and then we have a display like this. You notice that the formation of different bands. Okay, these are actually bands, the regions where hydrogen vapor absorbs light or colors of wavelengths that are associated with the region. Okay, when the bands move towards the red end of the spectrum, we say that the light has been red shifted. Okay, now what then is redshift? The increase in wavelength of light when light moves away from the observer is called a redshift, like what we have here. Whenever light moves away from the observer, there tends to be an increase in the wavelength of the light. That's a redshift. Now we also have a blue shift, which is the direct opposite of redshift. In this case, there's a decrease in wavelength because light is moving towards the observer. Now redshift can also mean the shift in the absorption lines in the spectrum of white light towards the red part of the spectrum. Okay, like when you consider these two bands, these two spectrum here, as a normal from a normal light and from a distance light moving away, you will notice that the bands here are moving towards the red side, towards the red spectrum. That is also a red shift. So light seen from distant galaxies appear red shifted. Okay, now in 1920, astronomers found out this evidence. Okay, they discovered that the galaxies that are furthest are moving faster because they are greatly red shifted. That is, the wavelength of light coming from them is much more longer. Okay, so from this evidence, they postulated this, that since galaxies are all moving apart from each other, moving far away from each other, moving apart, they must have kicked off or started from a point. Okay, that is, galaxies must have started off from a point before they move apart. Okay, like we see in this case, all the galaxies receding when you observe them. All the lights from this galaxy 1, 2, 3, 4, 5 are redshifted when you observe them from the Milky Way, from our own galaxy. Okay, it implies that they are all moving apart from each other and they must have kicked off from a point. Scientists observe that the wavelength of light given off from the galaxies that are moving away are longer than expected. And that is what we know, what is known as the redshift, which is a useful evidence of the Big Bang. Another evidence of the Big Bang is the cosmic microwave background radiation, which is the CMBR. The cosmic microwave background radiation is a faint glow of light that fills the universe, falling on Earth from every direction with nearly the same kind of intensity. Okay, it's like the residual light of creation. Okay, just like an afterglow. What happens after a glow? Okay, now this is similar to what we have in the picture here. You see an afterglow or after effect of the Big Bang. The light that is left behind, that's the glow that is left behind. Okay, so when you observe this, the universe, you notice a lot of this afterglow, which we call the cosmic microwave background radiation. This is similar to the case of heating a stove and then the stove radiating the heat back to the surrounding. Okay, the CMBR is an evidence that the universe is cooling off. It must have started with an intense temperature, like what the Big Bang says, the states. Okay, and currently now it's cooling off. That's another useful evidence that supports the Big Bang theory. A timeline for the universe. Now, the universe have so far moved through different stages to what we have today. Okay, 13.8 billion years ago was the time it was created, or it was formed, let's put it that way, or the birth of the universe. Okay, so the birth of the galaxies is about 13 billion years ago, and then the birth of our stars and planet, of our sun rather, and planet is about 4.6 billion years ago. Now, shortly after that, we have the creation of moons. Moons were formed about 4.5 billion years ago. Then we have a stage of heavy bombardment, and then the first life was formed at about 3.5 billion years ago. The life are basically unicellular, single-celled organisms. And then mammals appeared on Earth at about 200 million years ago. Then after that, we have the extinction of the dinosaurs, which took place at about 66 million years ago. Okay, our first ancestors, that is the ape, appeared at about 2.5 million years ago, and then Homo sapien, which is man, appeared at about 200,000 years ago, and so on. Now, the end of the universe. No one knows what happens to the universe after now. Now, there are lots of debate whether it's going to continue to expand or whether it's going to shrink back. Okay? Whether the expansion is going to get faster, or will gravity pull it back again? Or will it expand to a certain size and then stay that way? What's going to happen to the temperature of the universe? Will it keep dropping? Or will it get to the absolute zero? Now, no one can be able to ascertain that fact. This is because going by what we have, by the technology we have, we don't have the instrument so far to be able to determine the mass of all of the objects in the universe. Okay? It's not possible with our current technology. Okay, so we cannot say for sure what's going to happen, but perhaps as time goes on, knowledge is not static, it's dynamic. Maybe we'll find out more facts about the universe. So students, or guys, I want you to leave a like down below. Click on the like button there if the video interests you. And if there's any area you want me to adjust or to clarify, please leave a comment in the comment section. Have a nice day.